Hello, everyone. Have you ever had a thought keep you up all night? I'm sure for most of you the answer is yes, and that just happened to me. In fact, I did an entire version of this video without having the microphone on because I did this on 4 hours of sleep. Anyway, I needed to get these thoughts out. So the problem is the thought that I have is itself both super simple and super complex. It's simple in that the specific question is very easy to formulate, but it's complex in that to answer the question in a way that would make sense, there has to be a lot of background to it. So part of this goes back to the recent videos I've been making on the factor field. But more than that, it also goes back to this specific video by Matt Parker, and the link will be in the description. But specifically, I mean this section.
This is where you've got infinitely many, I'm going to use table tennis balls, and then you number them and you put them in a box. So this is table tennis ball number 1. And the only rule is whenever you put in a square number, you take out its square root. So I've put in 1, I'm going to take out its square root, 1. Now that only applies if it's a perfect square, so it's got a whole number square root. So when I put in 2, that can stay. And I'm going to put in 3, no problems. When I put in 4, however, 4 is a square number. So I put in 4 and I take out 2. And then I carry on. I keep numbering the balls, putting them in one at a time. And the question is, if I carry on doing this for the infinitely many countable numbers, once I've done all infinitely many of them, how many will be left? And the surprising answer is 0. Even though if you think about it, on every single step, I either put in a ball and take one out. So if I put in 9, I'm going to take out 3. Or I put in a ball and leave it there. So I'm going to put in 10. So it's always either staying the same or increasing. Yet, if I do that infinitely many times, either leaving the total number alone or increasing it, it ends up at 0. And you're like, well, that doesn't make any sense. There's no way that can be how it works. And once again, we're being tripped up by our human intuition because, and actually I've kind of set this up badly because by doing this one step at a time, I have to do it infinitely many times. And as we established before, that would take a very, very long time. So actually I could have rephrased this to say, I put in the first ball at like 1 hour to midnight. And I put in the next ball when there's half as much time left until midnight. And then the next ball, half as much, half as much, half as much. That means when it hits midnight, we've gone through the infinitely many halves. And I mean, right at the end, it's going to be chaos. There's going to be balls flying in. There's going to be balls flying out. But we will have infinitely many steps. And then right on midnight, bam, empty box. And once again, we're kind of thinking of infinity as just a very, very big number. But that's not how it works. We could actually reframe this. It'll make a lot more sense. Like imagine, first of all, you dump in every single whole number at once. There's infinitely many of them in the box. And now I'm going to dump out every single number that can be squared. Well, that's all of them. You can take any whole number and square it. So now I dump out all of them at once. And by doing it that way, it's way more obvious that you end up with an empty box. So the issue is, if you're trying to work out how big an infinity is, you can't just jump to the first conclusion. You've got to make sure you think about it very, very carefully.
Now, you might be wondering how that fits in with my recent videos on the factor field. Well, to be a little bit clearer, it goes back to more of what mathematical models are in the first place. Because in the end, that is the actual issue at root. We use mathematical models all the time, especially in physics. In fact, I've seen the following quote attributed to, I believe it was Galileo. Mathematics is the language in which God has written the universe. And whether it really was Galileo or someone else, it is very clear that mathematical models certainly provide a lot of useful information about the physical world. In fact, it is so useful that mathematics really has no business being that foundational to literally everything, and yet it is. In fact, I had a professor once describe it as the unreasonable amount of success with mathematical models. So let me just look at the first 10 rows of the factor field, and I'm going to do this manually in Excel for you right now to demonstrate my point. See, when I first created the factor field somewhere around 2008 or so, I made it in Excel, and I started in cell A1. But the fact that it starts at A1 itself already suggests a pattern being applied to the factor field. And the question is whether that ought to be applied there or not. Is it intentional or a mistaken coincidence? So let's scroll down here a ways and move over to this cell. I'm just going to pick it somewhat at random, and we'll just ignore the cells in the columns. We are just looking at the physical model of what we're making, not what that model might represent. And so I'll do that quickly for just the 10 rows. Again, the rules are simple. From this starting point, we count down 10 rows and fill in the background. Then we move over one to the right and we fill in every other one. Now every third one. Every fourth one. And now this repeats. Anything that would repeat would just disappear off the bottom, so we just do the diagonal the rest of the way. Now we've got our object. This is our physical pattern. It's just sitting there with no context. It just so happens that if I decide to call this axis the integers and this axis the factors, that it correlates to what we know of numbers. That is, if this row is 1 and this column is 1, then 1 is a factor of 1. And 1 and 2 are factors of 2, and so on. But again, that is just me applying this model to the numbers. And just like how mathematical models are unreasonably accurate in so many other ways, maybe this mathematical model just happens to be unreasonably accurate to describe this structure too. But now I need to confess something, a little white lie that I said at the beginning. I said that this was the pattern that I initially created for the factor field starting at cell A1. That isn't quite accurate. This is how I originally formed the factor field. So yes, I did start at A1, correct, but this was the actual pattern. As you can see, this is basically the same thing. It's the same pattern after that first row, but this is the actual first factor field I did, except that when I did it, I actually went for 100 rows manually. Yes, manually for 100 rows. You can see why I'm only doing it for 10 rows now, because the full 100 would take forever. Not that forever is really, you know what I mean. It's not forever. You get the point. I'm also going to remove this or it will continue to bug me. So on to the point. Now you can clearly see from this actual method that I used that this is the exact same version as the other version that I've been showing, except that it starts with this bar across the top. Now at this point you're probably thinking, oh, that's interesting, but what does that have to do with the section of Matt Parker's video you started this off with? Patience, my young Padawan, patience. See, if we look at the factor field as a mathematical model, we can clearly see how the factors representing the numbers 1, 2, 3, and so on are here. But what is this line here? I mean, it clearly follows that if these are the integers ascending in order, then this line would be 0, right? Now again, back when I first created the factor field, this presented a bit of a problem for me because in my head, I was using the definition of factors that, sadly, I was taught in high school. Basically, that definition was A is a factor of B if A divides exactly into B with no remainder. Turns out that that is not the actual definition of a factor. The actual definition is more along the lines of A is a factor of B if B equals some integer constant C multiplied by A. Now, with that definition in mind, it's clear to see that 0 would have every single integer as a factor. just like this line represents. But again, in 2008, when I created the factor field, I had a faulty misunderstanding of the definitions of factors. So in my mind, when I saw these other rows and I was thinking, well, look, 8 is representing 1 times 8 and 2 times 4. So that would mean 0 is representing 0 times infinity and 1 times infinity minus 1 and so on. And that doesn't make any sense. So I know what we'll do. We'll just skip this entire row completely and ignore it by starting the next line down. But now I want to correct that error because this bar at the top really does represent 0. And in fact, we can tweak the factor field code I made in Python to show what this would look like if we included the negative numbers as well. And I'm not going to go in depth on the code here. Suffice to say that if you want to copy it yourself and run it, you'll be able to reproduce this on your end. I might go into more detail in a future video, but for now, I've just wanted to create this graph. Incidentally, this graph now gives us ways to find the negative factors in addition to positive factors. So in reality, this is actually a more accurate representation of the factor field than what I've been showing previously. And there's a lot to explore in this graph. But let me connect this back to the main point and why I showed Matt Parker's video clip at the beginning of my video. So to do that, I'm going back to the Excel spreadsheet. This is the version of the factor field that I made a long time ago. So it's got thousands of rows created in it. And I was always interested in rows such as the one that's shown here. In fact, I think the first video I did on the factor field on this channel was about this number here, which is 10 factorial. Because it was in my super mega favorite number for that video playlist that James Grime did. Factorials are always interesting to me in relation to the factor field because they guarantee that these factors are filled out at the front. See, 10 factorial is multiplying 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. Those first 10 are guaranteed to be filled out on these columns. But wait a second, by that same logic, if we multiplied every single integer together, sort of like an infinity factorial, that would give us the exact same row we see at row 0. But row 0 is row 0, not row infinity 0. So is this an instance where the model of mathematics no longer fits the physical representation? I'm actually going to argue no. That actually is what you would get if you could take all integers, multiply them together as an actual number, and that reasoning is the same as what was put in Matt Parker's video, which he demonstrated with the ping pong balls. And here's why I say that. Look again at this line. This is 10 factorial. That means it represents row 3,628,800. Except if you know anything about Excel at all, you know that that is impossible. Excel clearly doesn't have 3.6 million rows in a spreadsheet. So what is this value actually? Well, let's think about this for a second. We need to have factors representing 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 to make this graph work, correct? But to have the factor, we don't need to have all of them as multiples. We just need the highest integer value with all the lower factors included in it. So in other words, we need the number that represents 10, and 10 carries along with it the factors of 2 and 5. So we don't need to include 2 or 5 in our actual number that we're looking at. So that will give us 362,880 when we multiply 3 times 4 times 6 times 7 times 8 times 9 times 10. Now that number is still too large to fit in an Excel spreadsheet, but because we have 9, that means we can take out the 3 and reduce the number to 120,960. And because we have an 8, we can take out that 4 at the beginning, and that gives us 30,240. And that number is the one that we're representing on the spreadsheet here. So instead of 10 factorial, we're looking at just 6 times 7 times 8 times 9 times 10. And that is sufficient to represent those first 10 factors. We don't need the lower numbers to create this bar that's here at the beginning of the graph. As you can see, that is the exact same type of reasoning that was described by the ping pong balls in Matt Parker's video. Yes, we're adding in more and more integers the farther we're multiplying, but we're also taking out more and more factors, because instead of adding an integer and then removing them when we're finding the square root of a higher number, we're adding integers and then taking them out when we find that integer is a factor of the higher number we're multiplying. It's the exact same process, and it will have the exact same result in the end. When you take n factorial to the limit of infinity, you get the exact same line on the factor field graph that you get at 0. Not just because of the definition of a factor, but also because that is how the patterns emerge from this structure. And because I recently went over Euclid's proof of infinite primes, let me just add this really quick. The same thing is true here. Think of how n factorial plus 1 means that a number cannot have any factors of any of those integers that make up the n. So if n is at the limit of infinity, that means the number 1 after that limit can only have 1 itself as a factor. It's the only possible factor it can have. So n factorial at the limit of infinity plus 1 gets you back to 1. What is 1 minus 1? You get 0 again, or n factorial at infinity. 0 has an infinite number of factors. And the only possible factor 1 more than it can have is 1 itself. And we know for a fact 1 is 1 more than 0. This stays consistent. And because it stays consistent, and because this result conceptually follows from the model of the factor field graph itself, and based on the concept that if two things that are exactly the same are equivalent, then that implies in some fashion that n factorial at the limit of infinity actually is the same thing as 0. And with all that, I hope you have a wonderful day.